For the next exam, we're going to have this material is going to be on chapter 7 and chapter 8. And today I'm just going to make it through section 0.8, which is basically half of the chapter. But there are quite a few slides. Okay, gases, liquids, and solids. So we're going to look at, first part is on the kinetic molecular theory, then we'll get through the gas laws, and then we'll, in fact, Dalton is one of the gas laws, and we'll stop right there. Okay, common physical properties of matter. We can measure these things fairly easily, actually. The volume and whether or not the object or the matter has a shape will determine how we classify it as a gas, liquid, or solid. And we can also measure the density, which we've done that in the lab. Compressibility is an interesting fact. Gases are obviously compressible. You can just, anybody that's ever filled up their own tire with a hand pump knows about compressibility. As a general rule, liquids and solids are not compressible, definitely solids. Liquids, we've discovered that liquids are slightly compressible. Measurements have been made at 1.5 to 2 miles down in the ocean. Found the density of seawater down there is higher, measurably higher than it is on the surface. Now, what's responsible for compressibility? How much space is there between the molecules? Right? Then you can push them closer together. In liquids, there's not a lot of space. In gases, there's lots of space. So compressibility makes sense for a gas. Thermal expansion. So you can measure the thermal expansion of material, and that can take a couple of different forms. There's what we call the coefficient of linear expansion, which references for a particular material. As you increase the temperature 1 degree at a time, how much longer will it get in relation to its original length? It's like a fractional increase. But you can also reference thermal expansion in terms of volume, and that makes more sense for gases and liquids because they need a container to hold them. So if you allow them to expand as the temperature increases, then volume makes more sense as a measure of their expansion. Okay. Actually, I already talked about this one. If we quantify compressibility, we say we measure the change in volume of a sample based upon the pressure. Right? So if we change the pressure increase it by 1 atmosphere, then it'll decrease its volume by a certain amount. Thermal expansion, similarly, will measure the change in volume when the temperature changes by a certain amount. So these are intensive properties. In other words, it really doesn't matter how much of the stuff you have. In other words, it matters what the matter is. Okay, when we talk about, and this came straight out of your book actually, when we're comparing the solid, liquid, and gaseous states, this is a table of comparisons. When we're looking at volume and shape, we find that solids maintain their own volume and their own shape. They need no help. No container required. Whereas liquids require a container for their shape, but not for their volume. And gases require a container for both the volume and the shape. As a general rule, solids have the highest density. Liquids have a high density, but it's usually lower than the solid of that material. There are some exceptions, and We'll probably talk about one or two of them in a few minutes. Gases have a very low density. In fact, their densities are measured in grams per liter rather than grams per milliliter or grams per cubic centimeter. Compressibility is, like I mentioned, small for solids, small for liquid state, and for all intents and purposes, solids are incompressible. I mean, I suppose under extreme conditions, you can get them to compress. There's talk of certain stars in the universe, like neutron stars, where they're so dense, 1 tablespoon of a neutron star would be several tons. So compressibility is possible for solids, but for our purposes, you can consider solids incompressible. Same for liquids. But gases have a very large compressibility. Thermal expansion, it's usually very small for solids, small but a little larger for liquids, and moderate for gases. Those values, you don't need to know those values. They're just for comparison purposes. So, at the very beginning of the semester, I made a major point of the difference between a law and a theory. The law just says, this is what happens under these conditions, where a theory tries to explain why that happens. And it's instructive to approach solids, liquids, and gases from a theoretical standpoint. In other words, if we understand the theory of why they behave the way they do, it makes more sense. Their behavior makes more sense. And this is the dominant theory about matter and how it behaves, is kinetic molecular theory. Right? It started off as an explanation for gas behavior, the kinetic molecular theory of gases, but it's since been expanded to include solids and liquids. It was easier to study it in terms of gases, primarily because under these conditions of surface pressure on the earth and room temperature, average temperature, most gases behave alike. You can't tell the difference from a physical standpoint. And we'll talk about that some more in a minute too. But the kinetic molecular theory has several postulates that must be accepted in order for it to explain things. One is that matter is composed of very tiny particles. Right? That seems like a no-brainer because we've been talking in those terms since the very beginning. But the theory, we're requiring the theory to put these things down in writing. Say, it's like when I worked for the government. If it's not on paper, it never happened. Maybe you've heard that one before. Matter is composed of tiny particles, sometimes atoms, sometimes molecules, sometimes ions. And they have a definite size. And those sizes do not change. So if we have a molecule of table sugar, it'll be like that. And if you have a molecule of water, it'll be like that. It's a different size and shape. They also have a different shape. And all of these things in combination, including what our discussion on polarity, contributes to their behavior, the characteristics that are assigned to these particles of matter. The particles are in constant and random motion. This is a requirement of the fact that we can't track every particle in the matter. There's just too many of them. Not even the biggest crazed supercomputer can do that. Even if we could track the momentum of every particle, we don't have enough computing power to put them all together into a final answer for what they're going to do and how they behave. So we have to approach it from a statistical standpoint. In other words, on average, how does the matter behave? And in order to do that, we have to assume that their motion is random and they're always moving. The only time particles in the matter is not moving, particles are not moving, is absolute zero. That's the condition of absolute zero in temperature. There's no kinetic energy, no motion whatsoever, not even vibrational motion. I mean, they don't sit there and jiggle at all at absolute zero. Consequently, at any temperature above absolute zero, each particle has kinetic energy, and that's energy of motion. And we can calculate that on an individual scale. If we know the mass of the particle or the mass of the object, it could be the size of a planet for that matter. And if we know its mass and we know its velocity, we can calculate the kinetic energy with this formula. Mass times, and we square the velocity. So in a practical sense, think of your car's moving down the highway at 30 miles an hour. And you press on the accelerator and you go to 60 miles an hour. You've doubled your speed. As long as you're going in the same direction, you've doubled your velocity. But what has happened to your energy? Your energy has quadrupled to go from 30 to 60. So that's why they say, safety engineers say, speed kills, simply because you've got so much more energy at high speed than you do at low speed. And in order to stop, in case you have to stop, ideally with your brakes, but if you hit something else, then you got to dissipate all that energy. And if you're going twice as fast as you were before, there's 4 times as much energy. Okay. So we also discuss how these particles interact. If they're in constant motion, eventually they're going to smack into each other. Now, this postulate normally is stated in terms that for ideal materials, the particles do not interact. In other words, when they smack into each other, they behave like billiard balls. Perfectly elastic collision. They just hit, bounce off. But in reality, there is some interaction. There's less interaction if they're moving very fast. Another high temperature decreases the amount of interaction because they don't have much time. Right? They're moving so fast, it's gone. No time to talk. But as they slow down, there's more time to interact, and you do see interaction between molecules in a substance. And it depends upon whether or not they have a polar character, largely. Sometimes it depends on, if they're very large molecules, it depends on their geometry and their shape. So when you get into biochemical interactions, those, you're talking about large molecules there, mostly, especially enzymes and their substrates when they come into contact, because the enzymes act as a catalyst. So they'll promote the reaction, and the shape is everything. But largely it's due to their polarity or lack of polarity. We can subdivide these interactions into 2 types. Let's see. They can either attract one another or repel, depending on how they're oriented. If you have a polar molecule, like, well, let's keep it simple, like water. It's shaped like that, and I think I talked about this. The bond itself is polar in this direction. That is, the electron distribution favors oxygen. And when you add them up, because of the shape, you get a polar molecule like that. Okay, so it's slightly negative on this side and slightly positive on this side. In fact, toward the hydrogens. So knowing that, when they approach one another, two water molecules approach, if they approach from this direction, there'll be an attraction, like that. But if they happen to approach from in this direction, right, there'll be a repulsion. Okay, so you can have both types of interaction. So that being said, there can be stored potential energy in these interactions. And it results from that position and the external conditions like temperature, pressure, and so forth, and what they're made of. Okay. All of these things jumbled together, and we have to treat them. Sometimes we can rationalize them based upon what we know of the molecules and their structures. But ultimately, we have to treat them statistically, because you're not going to have the same interaction between two molecules all the way through the system. Right? We said it's random motion, so it's going to be a mix. And this, they can store potential energy in those interactions. And the type of interaction that can occur depends on several things. Potential energy could be potential energy of position. That is, and this is not so much characteristic of matter that's just sitting there and interacting with their molecules. This is more what is the position of a molecule relative to some external field. The best example of that is gravity. Right? In a gravitational field, I have a certain amount of energy at this position, and we're on the second floor. So on ground level, I would have less potential energy because I'm closer to the center of the force that's attracting me. So there's stored potential energy in my position above the ground. All I have to do to get that energy back is jump out the window. And right before I hit the ground, I'll have that potential energy difference restored to me in the form of kinetic energy. I'll be moving, right? And then of course, when I hit the ground, that kinetic energy will be converted into some other form of energy, like broken bones and heat, or soft tissue damage. So that's potential energy of position. Condition is a little more difficult to wrap my brain around that. So we can say, actually, they're making an exception here, and or. So condition and or composition. In chemistry, composition is more important. Composition refers to bonding. There's energy stored in the bond between two atoms. Okay. And if you add energy to that bond, it takes a certain amount to break the bond. But then if a different bond reforms somewhere, you get some of that energy back. Sometimes you get less than, sometimes you get more than. So we're talking about energy stored, potential energy stored in the bonds here. Those two are the most important concepts: the positional potential energy and composition. Now that can occur in terms of electrostatics, like I mentioned here with the water molecules, either positives repelling or negatives repelling, or positives and negatives attracting each other. And this doesn't have to be charged particles. It can be partial charges. Right? But the easiest way to study it is with completely charged particles. like sodium and chloride ions in a cube of table salt. There's a strong electrostatic attraction there, and that's stored energy. In other words, well, actually, you store energy if you break those electrostatic bonds. When you think of stored energy, I think this is important. When you think of stored energy, like many things, it's all relative, right? Stored energy relative to what? Well, if your positional energy stored relative to the ground. Let's suppose I jump from 10,000 feet and I hit the top of the Empire State Building before I hit the ground. I've only got a certain amount of energy recovered from that position relative to the top of the Empire State Building. If I didn't hit the building, then I get more of that energy back. So it's all relative to what before and after, right? The final condition minus the initial condition. Now, one important concept here is not only does the charge not have to be complete, like an ion, like sodium ions, chloride ions. It could be partial charges like our water molecules, polar molecules. Those are not complete charges. Those are just slight redistribution of electron density, which adds some charge, but not a complete charge. Complete charge is when you take an electron and you transfer it from here over there, and it stays there, okay? But that delta, that slight charge, is just a way of expressing partial charge density imbalance in a molecule or a bond. But those, on average, those redistributions of charge density, those slight redistributions, are permanent. Once you've established them, they're pretty much there to stay. But we can also get instantaneous redistribution of electron density, simply because electrons are always on the move. But if the molecule is not, if we don't recognize it as polar, right? If we have, let's take a really simple one. Right? Nitrogen that you breathe in the air. It's the Lewis dot structure for nitrogen, dinitrogen. Right? That can't be polar because these two atoms are equal. Right? So the distribution is evenly distributed. But if that were the case, and if that stayed that way, then as you get colder, then you allow any possible interactions to take effect. The really weak ones come out and show themselves when you get cold. If you get this really cold, then you start to see interactions. And the evidence for that is that this gas will become a liquid at a certain temperature. So you know that there's interaction there, some type of attraction, right? But it can't be polar because the molecule is definitely not polar. So what happens is, in a split second, the electrons will tend to slightly redistribute to one side or the other. And that just takes a microsecond. But when that happens, any molecules in their vicinity tend to feel a push that way and a pull this way. So now we've established in a neighboring molecule for that instant a slight redistribution. And now you've got that attraction. And the evidence for that is liquefaction of this gas at a low enough temperature. Okay. So like I've always said before, nature just does what it does. It's our job to try to explain it. Okay, so you got those electrostatic interactions and kinetic energy, right? kinetic energy, due to this velocity of the individual particles, increases as the temperature increases. That just makes sense. When you increase the temperature, you've added energy to the system. And the energy manifests itself largely in terms of kinetic energy of the individual particles. Okay, so they're moving. And that being said, temperature is a measure of the average kinetic energy of that substance. Okay, so you can say with confidence, if the temperature of this substance is at, say, 20 degrees, and then we increase the temperature to 30 degrees, that we've increased the average kinetic energy of all the particles. Now, each particle might have slightly different kinetic energy, but on average, we've, say if we went from 20 to 40, well, no, that's not true. Kelvin. If we went from 100 Kelvin to 200 Kelvin, then we have doubled the kinetic energy. Okay. So when they collide, energy can be transferred by these collisions. And an elastic collision, anybody had physics? Okay. The definition of an elastic collision is one in which the kinetic energy before the collision is exactly the same as after the collision. You've lost nothing in terms of kinetic energy. Okay. And inelastic collision can be graded. It can be 100% inelastic or it can be partially inelastic. In that case, you do lose some of the kinetic energy in the process. But for the purposes of this theory, all the particles experience elastic collisions. Yeah, think billiard balls. Anybody like to play pool? No? Okay, that's all right. It takes a geometric eye to be good at pool.
My husband's neighbor's great at it. They constantly play, but I ain't got patience. I play, but I'm not good. I've
Yeah.
played before. So.
Oops. Oops, what did I do? Accidentally pressing that button, right? Let's get back to the kinetic. Here we go. Okay. So with that in mind, let's think of solids, liquids, and gases in terms of a balance between their potential energies and their kinetic energies. If the, okay, looking at kinetic energy is actually a disruptive force. It tends to make the particles of the system more independent. So the higher the kinetic energy, the more independently they behave, right? And it's like I said before, if they got more kinetic energy, they're moving fast, moving faster. That means there's very little time to interact. They behave more independently from one another. Whereas potential energy is, can be considered a cohesive force. It tends to cause stability. In other words, particles tend to group together. So when we say kinetic energy, we're measuring, well, they call it a disruptive force. I would call it an adhesive. Excuse me. Yeah. No, that's not right. Disruptive. Let's leave it at that. Disruptive force. And potential energy is cohesive force. Actually, the definition of cohesive is attraction between like particles. So cohesive could be described in terms of, I don't know, what holds water together in a glass of water. Right, they're all the same molecules, so there's cohesive force. But adhesive forces are describing attraction between unlike particles. So when you when you put a Band-Aid on, the Band-Aid adheres to your skin. They're obviously not the same material. Okay, those are adhesive forces. Okay, two types of energy that are possible for matter, kinetic and potential. That is true. When we describe the energy content of any substance, we can describe it in terms of its kinetic energy and its potential energy. Okay, now let's talk about individual physical states. The physical state we identify as a solid, one in which the shape and volume are fixed and independently maintained by the substance. That physical state is characterized by potential energy as a dominating force. The cohesive force is holding it together. That's the dominant force. And the disruptive force is less. All the time. So let's look at it this way. For a solid, the cohesive force is much greater than the disruptive force. Okay. Most often, the particles occupy a fixed position. And if they have any kinetic energy at all, it's energy of vibration. Right? They just sit there jiggling. Right. So this is supposed to illustrate that. It's supposed to a vibrating solid. We mentioned this already. Definite volume, definite shape, high density. The molecules, the particles are very close together, so that gives them high density. Right? If you have definition of density, remember, mass per unit volume. So if you want this to go up, you have two choices. You can add more mass, or you can decrease the volume, or both, and you can increase the density. Okay. Small compressibility, because there's not much space between the particles. I mentioned that earlier. Okay, very small thermal expansion. That is, increases in temperature while they increase the kinetic energy, this disruptive force. So as you increase the energy, you're starting to add more disruptive force. And that's more vibrational motion. And when a particle vibrates, it's banging up against its neighbors, right? And they'll move out until they hit somebody else, or they'll just move out and come back. They're kind of in a harmonic motion like that. And that adds more space, which causes an expansion. But it's not much. The strength of these cohesive forces is such that it keeps that volume from expanding a lot with temperature. That's characteristic of solids. Liquids. In a liquid, the potential energy and the kinetic energy are somewhat in balance. Okay, so we can say for liquids, they're approximately equal, potential energy and this disruptive kinetic energy. They're still close to each other, but think of them as not fixed in their position. They're able to slide past one another. That's why they can't maintain their own shape. They're close enough, and the cohesive forces are strong enough that they can maintain their volume at a given temperature. But the forces are not strong enough so that they will hold their shape. So liquids have to be placed in a container. So there you are, a liquid in a beaker. I've already mentioned all this stuff. Let's move on. They still have high density, simply because they can move past one another, but we haven't added that much. When you go from a solid to a liquid, you've not added, you've added some space, but not a lot. So they're still high density. And in fact, some liquids are higher density than other solids. Mercury is a perfect example. Mercury is a liquid. But if you compare mercury to, let's see, where's mercury? Mercury, here it is. Mercury to, say, lead, I'm not sure about their densities. I think lead is more dense, but not by much. And that's largely due to the fact that the lead atom is a heavier atom than mercury. But lead as a solid at the same temperature as mercury as a liquid, there's not a whole lot of difference between in terms of their density. They're not very compressible, right? Those molecules can move past one another, but that doesn't create a whole lot of space. Creates some space, a little bit of space. So if you put them under pressure, you can get them to compress, but it's a very small change in volume. They don't have a very high thermal expansion either. A lot of their motion is vibrational. They can only move a short distance, even if their translational motion from one place to another is not very much, because they're so close together. I mean, they'll move a femtometer smack into somebody. Okay, so there's not a lot of space, and that keeps them from acquiring a lot of translational kinetic energy. They still have the vibrational part. But that being said, if you increase the temperature, they will expand somewhat. And evidence of that is your thermometers. Right? When you stick your thermometer in hot water, you watch that. Well, ours have a red liquid in it. The red liquid will move up. That's a sign of expansion of that liquid. And the reason it moves so far is because it's expanding volume, but we've narrowed that channel down to a little capillary, hair thin. So if it expands just a fraction of its original volume, it'll move a long way. Okay, gases. Now, gases are just the other way around. The disruptive far outweighs the cohesive in a gas. So much so that you can almost treat the cohesive as zero, no effect at all. And that's under conditions of reasonably high temperature, which is room temperature, and low pressure, which is 1 atmosphere pressure. And those conditions, the cohesive forces are virtually non-existent, very weak, and can be considered zero under those conditions I mentioned earlier: high temperature, low pressure. They effectively are independent of one another. Okay, and there's lots of space between the particles in the gas. Massive amount. Relative to the size of the individual particles, these are many orders of magnitude. Based upon their size, there's lots of room. That's why when you put, well, we haven't talked about solutions much yet. We're talking about homogeneous mixtures. When you put two or more gases together, they always form a solution, a homogeneous mixture, simply because there's plenty of room for everybody. They don't even have to interact. They just move into those spaces. Okay. As a consequence, gases have an indefinite volume. They cannot maintain their own volume. And they obviously don't have a shape. So they always have to be contained. You know, it wouldn't make any sense to blow up a party balloon with a hole in it. It wouldn't hold the gas. Okay. And as a consequence, when you put a gas into a container, if there's nothing there before it, it will expand to fill that space. No matter how big the space is, it will expand to fill that entire space. I had a professor once who he was trying to make a point of, he was talking about statistics and probability. He said that there's a very slight, infinitesimally small probability that all the air in this room will migrate to that corner and will suffocate. He was just making a point. All right. It's never going to happen in our lifetime, of course. Probably never happen. But it just illustrates the fact that when we're talking about statistics, anything's possible. So you have to be careful with statistics. What's the saying? There are lies, damn lies, and statistics. In that order. And as a consequence, they have very low density. So if the particles, if you have particles in there with lots of space between them, then that occupies a certain volume with low mass, because the mass is guaranteed, is associated with the number of particles. So here's an illustration of compressibility. Right? It's fairly easy to compress a gas because there's lots of space. And notice you have the same number of particles, but they're just closer together. So gases are very compressible. And they obey a specific law, which we'll investigate in a few minutes, if I don't take too much time talking. They have moderate thermal expansion. Increases in temperature will increase the particle velocity, which increases their kinetic energy, which means when they hit each other, they tend to move apart. So the faster they're moving, the higher the temperature, the more space they want to occupy, and the more collisions that they will experience, impacting each other and the walls of the container. They have to impact the walls of the container. Otherwise, we wouldn't be able to measure their pressure. And we just add more space. Okay, these are the three physical states we've talked about so far. Now let's talk about the laws that govern gas behaviors. These laws, historically speaking, gases were investigated first in terms of modern science. And the reason for that was twofold. One is that under these conditions that we experience right now, most gases behave alike. So you can investigate any gas you want and it'll respond similarly. And there was also a limitation by technology. How do you study something when you don't have the technology to study it? So that had to develop along with the development of these gas laws, and we're going to look at them in order, chronological order, because of that limitation due to technology. When we're describing a gas, we need to know 4 conditions to describe it physically. Now, we're not talking about gases so much from a chemical standpoint, but from physical. If you know the temperature, you know the pressure on the gas, you know its volume, and you know how much of it there is, right? That's my abbreviation for moles. Okay. So if you know these 4 factors, you can describe a gas completely in its physical characteristics. And that's what the gas laws do. They use a combination of these factors to describe how a gas behaves under certain conditions. All right. So first of all, we need to define some things. Like, well, we know temperature already, and degrees Celsius is a common unit of measure for in the SI system. But when we're talking about gases, when we describe gases, we need an absolute system, right? Did I talk about how Kelvin developed? Okay, good. So what we need to do there is add 273 to it, and that gives us Kelvin. So that is the temperature description in terms of Kelvin. Pressure is a little bit different. The definition of pressure is force per unit area, right? So it's an intensive property. In other words, if you've got a certain value of pressure, then if you increase the area, you have to increase the force to maintain that pressure. And it doesn't matter how much you have of either one. If you want this to be constant, then if one changes, the other has to change. That's an intensive property. And there are a host of different ways to describe pressure. The SI unit for pressure is the Pascal, 1 Pascal. And the reason the Pascal is valuable is because it is interconvertible with other standard units in the SI system. Okay. But it's not very useful for us. So you just need to know that that's true. And perhaps a unit conversion will be introduced later. But what we're more interested in is this one, 1 atmosphere. 1 atmosphere is the average pressure at sea level. Now, of course, that can vary, right? If you measure the pressure at sea level, so we had to sort of standardize it. And the standard pressure of 1 atmosphere is also equal to 760 millimeters of mercury in the Torricelli barometer. Did I describe that one yet? Torricelli's barometer?
Don't think so.
Okay. Let me take a look at my hard copy and see. I don't want to steal my own thunder. If it's going to come up in an illustration, then I don't want to talk about that yet. There it is. Okay, it's a couple of slides down the road. So just stick that in the back of your head and remember it, and it'll show up in a few minutes. So, and in honor of Torricelli, a millimeter of mercury is a torr. So if you see a number in front of torr, that means millimeters of mercury. Also, 1 atmosphere is equal to 14.7 pounds per square inch. Okay, pounds per square inch is common in this country as a measure of pressure. In fact, any tire gauge you use will be calibrated in pounds per square inch. And that's force per unit area. And next week when we do our lab, we will measure pressure on a gas with a tire gauge. So you need to be able to convert it after you measure it, convert it into atmospheres. Okay. All right. Well, the only one that actually contains these units of force per unit area is pounds per square inch. Oops. Well, okay. Units of pressure, actually, that's not true. Kilogram per meter square, that's not true because kilogram is mass, not force, correct? Okay, we need a force. So force in the SI system is the Newton. So a Newton per square meter is equal to 1 Pascal. And then you have to say, well, what's a Newton? Right? So a Newton is pays tribute to Isaac Newton, and it's his second law of motion that is used to derive that value. Right? Force equals mass times acceleration. Okay? So 1 Newton, in honor of Newton, the force, is equal to kilogram, and then acceleration is meters per second squared. Acceleration is a change of velocity. Velocity is meters per second, and if it changes a certain amount per second. So that's why we have a second squared down here. So a kilogram meter per second squared is equal to a Newton. So we could substitute in here kilogram meters per second squared. And then this meter is in the numerator, that was in the denominator, so that one cancels. One of those cancels, and this one's gone. So it's like a kilogram per meter second squared. The only reason that you would need to know that is if you had a calculation that had units in it that could potentially cancel. And if you're using newtons and you have meters in here somewhere, and you can't cancel them unless you know what newton stands for, then you can substitute for the newton and reduce your units, mathematically speaking. Okay. So this pressure of a gas is a measure of the force on a certain area of the container that's exerted by the gas inside that container. Okay. All right, here's Torricelli's barometer. What Torricelli did was, and this is one of the first major breakthroughs in technology, the ability to measure gas pressure. Torricelli was measuring atmospheric pressure. Right? So he took a glass tube that was open at one end, closed at the other, of a uniform diameter. And at this time, when Torricelli was active in the late Renaissance, they knew very well how to make tubes, glass tubes of uniform diameter. They were very good at it. So they just closed off one end and filled it with mercury. So I have open end up here, like this. And he just filled it with mercury. Why did he use mercury? Well, he thought about using water, but he soon figured that if he used water, or maybe he even tried it, if he used water as his measuring medium, the atmospheric pressure would support a column of water 33 feet high. That would be kind of unwieldy. So he decided, okay, I need something more dense, but it's still a liquid. And mercury was perfect. Mercury was well known in the Renaissance, in fact, before the Renaissance. And in fact, some people thought it had medicinal qualities, and they would consume it. Anyway, it was readily available. So he had this pool of mercury. It's going to be like that, concave meniscus. And he filled this up to the top and put his thumb over it. And then he inverted the glass tube, and it would only have to be, 760 millimeters or higher for 1 atmosphere. And then he took it and submerged his hand in the mercury and turned it loose. And then watched it. And what happened? Well, the level dropped here, dropped in that glass tube. And then it stopped. What he had done was he created the first vacuum. Right? If something's there 1 second and it's not there the next second, then there's nothing there. It's a vacuum. But he reasoned that something was holding this column up. Right? It wasn't the pressure from the mercury, right? But this column had a certain mass and it exerted a pressure. And it was being held up, he reasoned, by the Earth's atmosphere, the gas above it. It was thick enough that it bore down on this column with enough force to hold that column up. And he used it to measure changes in air pressure. He could throw it in the back of his ox cart and head down to the ocean. and he noticed that the column went up, more air pressure. Or he took that same cart and went up a mountain, and he saw it go down. So that was confirmation of his summation that the atmosphere was responsible for that. Then he just sit it on his desk and leave it there and watch it over time. And pretty soon people realized that if it was dropping, sitting there and just dropping, bad weather's on the way. Or if it was rising, either bad weather had just disappeared or you can expect good weather. So high pressure versus low pressure, we still use that today as an indicator of approaching weather systems. Okay, so now we had a way to reliably and reproducibly measure air pressure. But there were modifications that could be done. You could take this barometer, and if you encase this, seal it off, so that now the only thing getting in there is gas pressure from some other vessel. Like that. So you got gas in here, then you can measure the pressure of that gas. And that's known as a manometer. And we use that principle to measure blood pressure. Okay. We have a cuff. It's a sealed system, and it's tightened around the arm, and it is sensitive, and it's flexible, and it's sensitive to pulses in your blood pressure as your heart beats. And you'll see it move here. Right? So we pressurize the system around your arm so that as your arm beats, it pushes on that gas, and you let it go gradually. And you listen. You listen for it. Have y'all done this in lab? No?
Well, we done it in anatomy.
Yes.
Yeah,
Okay. Anatomy. Okay. So you listen for sounds. I believe there are 5 of them. They're called Korotkov sounds. You listen for 2 in particular. And where the one first, that sound first appears is your, not diastolic, the other one. Systolic, thank you. Systolic, high pressure. And then you go down and you still hear some of those other sounds, and they go through changes. But when it disappears at the bottom, that's your diastolic pressure. And you just read it here. It's measuring the compression of this gas in here against your arm. Now, blood pressure could be measured directly. Right? You can put sensors. My wife had it done to her one time. They were trying to decide, does she have pulmonary hypertension? So they went in, I think they went in through a femoral artery. They went up, threaded this device to her pulmonary artery, and it measured pressure directly going into the lungs. She didn't have it, of course, but you can do it that way. That's an invasive method. Okay, so we got a way to measure pressure now. Volume is fairly simple to measure. The standard unit there is liters. And this one comes later. We'll talk about that one later, I hope. If I don't take too long. So these are the 4 variables that will describe completely a gas condition. Now let's get to the laws. The first one was volume is easy to measure, and now pressure can be measured. So Robert Boyle was an Englishman, and he measured the relationship, quantitative measure of the relationship between pressure and volume. And the other factor that you have to consider is that if you're going to let 2 of these vary so you can see how they relate to one another, the other 2 must be held constant. In other words, this would have to be constant, that would have to be constant. Then you can let these 2 vary. And when you do, what Boyle discovered was the pressure times the volume is always equal to a constant value. Okay? Now, how did he do that? Let's see. Do I have that in the picture? No. Boyle used a J tube. There's another one of those glass tubes, only they bent it into a J, like this. Open at this end, closed at the other end. Okay? And he also used mercury. So he added mercury to this tube, and he collected at the bottom. And he added some more. Okay? Eventually, he added enough to where it touched the inner curve of that tube. At that point, he had trapped gas in here. And that meant that the number of moles was fixed. And if you conduct the experiment quickly enough, then you can assume that the temperature is fairly constant. I mean, if you want to be absolutely certain, just submerge it in a bucket of water. Water doesn't change temperature very fast. So that will guarantee that it's fixed temperature. So he just kept adding mercury. And what he discovered was he adds mercury and it may go up to here on this side, but it's up here on this side. Okay. So he knew, since they weren't equal, that something in here is pushing back. There's a force being developed by the compressed gas. And the difference between the two heights, that height was a measure of the pressure on that gas. Well, plus atmospheric pressure. So you have atmospheric pressure plus the measurement of the mercury pressure. Then that's the total pressure in the gas. Okay. And he had a separate barometer over here to measure this one. So he could add them together. He noticed then that as he increased the pressure, kept adding mercury here, then the volume of the gas decreased. But if you multiplied the pressure here times the volume there, you always got a constant value. Okay, these are inversely related. That is, as the pressure goes up, volume goes down. It has to be that way. For this to be constant, if you make this one go up, that one's got to go down. Anytime you have a quotient, a product equal to a constant, it's an inverse relationship. Okay. So when you graph this data, right, he was changing the pressure and measuring the volume. So the pressure is the independent variable, and the dependent variable is the volume. When he plotted these values, he got that kind of curve. Right? As the pressure goes up, volume goes down. This is a special kind of curve. In math class, you may have heard of it. It's called a hyperbola. Hyperbola is special. It will keep going. If you follow it far enough, it will never touch this axis. If you follow it far enough this way, it will never touch that axis either. Okay, that's characteristic of a hyperbola. And the reason for that is pressure times volume equals constant. So if this is a real value, you can never make V 0. Right? V would be, if V were 0 and it touched this axis, then K would become 0. And we've already established that it's a constant value. So no matter how small it gets, it can't be 0. Okay, so that's Boyle's law. Now, this is the form that we use because that constant will vary with every experiment. It will be constant for the experiment, but it's difficult to use. So we use this format. I call it before and after. If you say the experiment is this pressure times this volume equals some constant, right? And then you change the pressure. Now you're going to have this pressure times this different volume is equal to that same constant, isn't it? Right. So it's a mathematical identity. If these are equal, both equal to the same constant, they're equal to each other. So that's what we're saying here. So if you know the pressure before and the volume before, and you have a new pressure, then you can solve for that unknown. Like any math equation, right? If you have one unknown, you can solve it. Okay, so that's Boyle's law. And this is just an illustration. If we measure the pressure here at 100 millimeters of mercury, we increase the pressure. If we double the pressure, then we cut the volume in half. And here we doubled it again. So we cut the volume in half again. But from here to here, we went 4 times the pressure. So it's 1/4 of the volume. So either way, you get to the same answer. Okay. That's the one we use most often. P1V1 equals P2V2 for Boyle's law. In the interest of time, well, okay. When you're solving a problem in the gas laws, look to see if it's given you before conditions and after conditions, and then see which one's missing. That'll tell you which law to use. Okay. At this point, we've got 12.4 liter gas at this pressure, and then we change the pressure from this to that. What's the volume after that? So it's important to identify which one's which. Otherwise, if you put them in the wrong place, you get the wrong answer. So the beginning pressure is 0.956 atmospheres. And that volume associated with this pressure is 11.4 liters. And we want to go to a pressure of 1.20 atmospheres. So there's your unknown. Now you can put your values in the correct position. And as long as these values are the same, pressures in atmospheres, then volume will be in liters. You could make this milliliters, then your answer would be in milliliters. Okay. Simply because it's a ratio. As long as the units cancel in your ratio, then you use the right units. You couldn't make this one liters and expect this one to be quarts. It just wouldn't work. So there you have it set up, and we find out that the volume now would be 9.88 liters instead of 12.4. So as the pressure went up, the volume went down. Okay, next comes Charles' law. Charles was a Frenchman, and he came along about a century after Boyle. And the reason was for the delay was the fact that we didn't have a reliable way of measuring temperature. The temperature scales had not been invented, or at least perfected, so that they could be relied upon by any scientist anywhere who could repeat the experiments. So once the temperature scales were finalized, and that also included the development of the Kelvin system, the Kelvin temperature, because while we noticed that this volume temperature relationship is always constant. So as the volume goes, as the temperature goes up, the volume goes up, right? It's that expansion of the gas. Am I about out of time? Oh, okay, okay.
You have that energy. Good luck. You have to let us know how it goes. Tell us how it goes.
I can only do my best.
Tell them you're becoming a chemist.
Yeah. I don't think you want any of us to be chemists.
No, that's not my goal. My goal is to give you enough chemistry to help you do something else.
Now, next semester, we do have to take a lab chemistry. We do have a chemistry class for our MLT program we have to take.
Yeah.
And we have that next semester, so,
Okay. Well, hopefully it won't be quite a shock if you get through this one, okay?
yeah, if we get through it.
Real quick, you said as the temperature goes up, the volume goes up?
Yes.
Okay.
The relationship, if you have two variables and they're in a quotient like this, equal to a constant, it's always a direct relationship. As one goes up, the other one has to go up in order to maintain that constant. So if we graph this, which Charles did, he changed the temperature and observed the volume. Then he noticed on gases, he got a linear plot. As the temperature goes up, the volume goes up, right? And it's a straight line. And the slope of this line is equal to that constant, right? All you have to do is say, all right, let's put temperature on this side. So if it's in the denominator over here, it's in the numerator there, equals KT. So they have Y equals MX, well, plus B. And then B in this case could be anything. If you're in the Celsius, if you're using Celsius, then it'll intersect somewhere up here. If you're using Kelvin, it'll always go through the origin because Kelvin is 0. Okay, that was Charles. Now, we can use the same reasoning for Charles as we did for Boyle, and V1 over T1 equals V2 over T2. Okay, before and after situation. Why am I making such a deal out of before and after? Because sometimes you don't know the before and after for a situation. You only know its current state, and there's a solution for that also. So before and after, I'm going to give you all the befores and afters laws, and then we'll work out the state. Right? If you don't know how you got there, but you have these data, then you're not stuck. You can still solve the problem. Okay. So that's your author's idea of understanding Charles' law. And in order to use this, temperature must always be in Kelvin. It has to be Kelvin. That's the only one that we're really picky about with these gas laws. It has to be Kelvin. Okay, so we can say before and after. Let's see, is this before and after? 1.30 liters of air at this temperature placed in a beaker containing liquid nitrogen. At this temperature, what will the volume of, yeah. So you're going from this temperature to this temperature, and we want to find out what the volume is. Actually, that is, let's say we have a container, a dewar. You know what a dewar is?
Yeah.
It's a thermos bottle. Remember the old thermoses? They have a vacuum in here. And they keep stuff really hot or really cold for a long time. So that's what we use to put liquefied gases in. We want to study them. So we have liquid nitrogen. The temperature of liquid nitrogen is minus 195 degrees C. So that temperature must be in the vapor above it, which is which is a valid storage temperature for some samples. They don't want to get it this cold, so they put it in the vapor above it. So that would be, so it's not really in the liquid nitrogen. Okay, so what would the volume be? You just be sure that you put these values in the correct place, and then you can solve for that answer and change your temperatures to Kelvin. We'll have some problems to work out. some of your homework problems, and then when we do a review, I'll do a review like I did before with, not with the homework problems, but with problems that look like what you'll see on the exam. I think that helped this time.
Yeah, I think so too.
Okay. Wait a minute, I left one out. I left a very important one out. Hold on a second. We're gonna pick it up later. No. Ooh, that's a slap in the face to Avogadro. Avogadro's law. It's not there. So I'm going to give it to you now. So Charles was temperature and volume, so we had to hold pressure and moles constant. Volume and moles is Avogadro's law. So that means this one and that one have to be held constant. Okay, so how do you hold pressure constant and allow volume to change? One of the best ways is to have a cylinder with a piston in it. And you have a mass up here of some kilograms bearing down along with atmospheric pressure, and it's constant pressure. And once you've trapped and constant temperature, then you've got a certain number of moles of your gas in here. And if you put more moles into it, it'll cause the volume to increase. So increase moles, increase volume. That's Avogadro's law. And you can say V1 over N1 equals V2 over N2, just like before. I'm gonna have to slide that. I'm gonna put that slide. I'll have to create a slide for that one. Okay. There's a whole story behind Avogadro, but we don't have time for it right now.
So it's a constant pressure and constant temperature. So if you're holding it down, just to make sure I'm correct, that if you add more of the moles, your volume is going to go up. If you decrease the moles, the volume is going to go down.
Exactly right. Okay. So this is a version of the combined gas law, but it doesn't include Avogadro. So what we should do is say, all right, how do we get started? Well, let's start with Boyle's law. P1 V1 equals P2 V2. And then we introduce Charles' law. So what's the relationship of V to temperature? It's that. Okay? So this also introduces a relationship between pressure and temperature too. If the volume is constant and the moles are constant, then you increase the temperature, you increase the pressure. Okay, that's not a separate law, but the relationship is still there and it's true. Now if we introduce Avogadro, volume and moles, there we go. So now we have this one. If pressure and temperature are constant, and you just do that, then you have a volume moles relationship. Or if, let's see, moles and pressure are constant, you have Charles' law. So this encompasses all of the laws together. This is the combined gas law. Okay, and that being said, if you know before conditions and after conditions, and all of these can vary if you're using this law, as long as one of them is unknown, then you can solve the equation. Like, yeah, the pressure change from here to here, volume change from there to there, mole change from here to here, we can say, and the temperature starts here, we can say what the temperature will be. Just all you need is one unknown. That's math. Here's an example. We're solving for this temperature. With these conditions, pressure change, volume change, pressure, volume, and we want to see how the temperature changes. So what we've done here is we said, all right, there's the temperature in Celsius, we had 273. This is the temperature in Celsius, we had 273. So by setting it up this way, when we solve the equation, our temperature is in Celsius already. Okay. Now, let's leave that one up there. How would we get to this point? If we use the same logic as our P1V1 equals P2V2, then this would be equal to a constant, and that would be equal to a constant, the same constant, right, in order to be that. Well, let's see. What is that constant? Well, if you fix the units of measure for each one of these and the value that's associated under standard conditions for each one of these, you can fix that value also. Okay, so let's do this. If the pressure is 1 atmosphere and we have 1 mole of gas trapped and the temperature is standard temperature for gases is 0 degrees Celsius. So that would be 273 K. Okay. What would be the volume under these conditions? Well, we'd have to measure it. And if you measure it, this ideal gas, we're still talking about an ideal gas, is 22.4 liters. So all these conditions relate to one another. And using these units of measure, K, we give it a special designation, is R, and that's equal to 0.08206 liter atmospheres, right, per mole K. Okay? As long as we use those units of measure, then that's what the K equals. Now that you know what K is, if you use the right units of measure, you don't have to know how you got there. Most often you'll see this equation written as P times V equals moles times the gas constant times temperature. PV equals nRT. So if you have if a situation is described in terms that are not before and after, in other words, it only gives you one temperature, it only gives you one volume, it only gives you one pressure, then you can solve for moles. That's your state function, not the before and after function. And this is the one we'll be using. I write 8206, they write 821. They just rounded it off here. Either one will get you close enough to get the correct answer on the test. And I made a point of the fact that standard temperature and pressure for gases is 0 degrees Celsius in 1 atmosphere. For most chemical reactions, when you see STP or standard temperature and pressure, 1 atmosphere is still true. But for other chemical reactions, 25 degrees Celsius is standard. But when we're working with gas walls, it's always 0 degrees. Sorry about that. I don't know how it happened, but that's it. It is what it is. Okay. So here's an example. Automobile tire at 23 degrees with an internal volume of 25 liters, filled with air at 2.18 atmospheres. Determine the number of moles of air in the tire. So we're only given one unit for each one, and we're asked to solve for that. So we have to make this Kelvin. This is liters, that's good. And how do you know what units to use? Well, you look at the R, the constant. We need liters, atmospheres, moles, and K. Because R pops up in all kinds of equations. And the units of measure for R are different for some other equations. So you just have to know what that is, or what the equation you're using, and which one to use to solve the problem. But for now, for the gases, this is it right here. We're going to keep it simple. All right. So if we solve our equation for moles, we know that we have 2.24 moles in there, in that tire. All right. In this case, we have volume in liters. We have temperature that has to be converted. And we have 5.67 kilograms of helium. We don't have an equation that works in kilograms, so we'd have to convert this to moles. So that would give us moles, liters, temperature. We can solve for pressure, as long as we convert that to moles. Okay. First, convert it to grams, and then use molar mass of helium converted to moles. Right. It's like I said at the very beginning. A lot of chemistry problems can be solved with dimensional analysis. In other words, units. Keep track of your units. As long as you're not violating any chemical laws, then dimensional analysis will get you there. And that's what it would look like. Here we're converting to grams, and then this is the molar mass. So this gives you moles. There's your R, there's your T, there's your V. Solve for P. Okay? Okay, last law. John Dalton. John Dalton was a British researcher. He did a bunch of things. In fact, he introduced the modern atomic theory, which we haven't got to yet, but, or did we? Did we do Dalton? I can't remember if we did him or not. Anyway, he also came up with this one. The law of partial pressure. All it says is, when you measure the pressure of a mixture of gases in a container, the total pressure there, that is due to the pressure of each individual gas, what's known as the partial pressures. All the way out to however many you have, doesn't matter. So each one contributes its own pressure. Okay? And we know from Avogadro's law that this pressure can vary with the number of moles. So if you know the relationship of this fractional pressure to the total, you also know the relationship of this fraction of moles to the total moles. Right? So if you measure, if you know the number of moles of all of these, of each of these gases in there, and add them up, they would be proportional to the total pressure. Right? That's using Avogadro and Dalton. So this just illustrates the pressure of this gas would be like 3 units, and this one would be 3, 6, 9 units. This one would be 2, 4, 6 units. Then the total pressure would be, well, I guess, if that's considered 1, then this is 3 times as much, and this is twice as much. Okay, so total is 6 times. Okay. So if we have a gas mixture consisting of oxygen, helium, and nitrogen, let's see. And let's do it this way. We have oxygen, right? Diatomic, helium, and nitrogen, also diatomic. Those 3 gases. And the total pressure is equal to 780 millimeters of mercury using Torricelli's barometer. It's not too common to see a mercury barometer anymore. I've got one on the Greenbrier campus at New River in my lab up there. I'm always afraid somebody's going to steal it because they're so rare and expensive. But it is what it is. So what's the partial pressure of oxygen if the partial pressure of helium and nitrogen are 86 and 124 together? So 86 plus 124 plus pressure of oxygen is equal to what? 780. So we can find this one. All we have to do is subtract those two away from that one, and that's the one that's left. And that would be 570 millimeters of mercury would be the pressure of oxygen. Okay, there's a practical application to this law. Sometimes when we're investigating chemical reactions, we want to capture the gas that's generated by that reaction. And one way to do it is to use a pool of water, and our reaction vessel is over here, and we pipe that water, that gas produced in here, and then we have a graduated cylinder here, like that, and it's full of water to the top. And then as the gas is generated, it collects up here. So it'll produce a measurable amount of gas in that space. But you have a gas coming in here, but what's it doing when it bubbles through water? It's picking up water vapor. So you actually have two gases in there. You have your gas, plus water vapor. Okay, so but you don't want water vapor in your measurement. So if you know the temperature, there's a table that'll tell you what the vapor pressure of water is at that temperature. And you can measure the total pressure and subtract it. Subtract the pressure of the water vapor from the total, and now you have the pressure of your gas. So that's a practical application of Dalton's law. And this is a problem that actually involves the use of two laws. Here you have a gas at 2 atmospheres pressure and 9 liters here with a valve in between. And this one is 3 atmospheres and 3 liters total volume. So what's going to happen when you open that valve? Right, the higher pressure is going to push gas into this one. Eventually they'll equilibrate and you'll have equal amounts throughout. But what will be, qualitatively speaking, where would you expect the pressure finally to settle for that whole system? Somewhere between this one and this one, right? Okay. So how do we calculate that pressure? The easiest way to do it is to treat them separately. Treat this one as itself with a vacuum over here. And then that tells you what's the pressure of this gas in that space. And then treat this one with that as a vacuum. And that tells you the partial pressure of this gas in all that space. Then you can add them together using Dalton's law and find the total, the final pressure. Okay. And we can do that. Let me see how many more slides we got before I have to pause. Oh, that's it. This one, and then we're, I think. Yeah, okay. So I don't have to write it on the board. So we're going to use the final volume is going to be the same for both of them. And so we know that we need 12 liters for our final volume. So initial volume, if we start here, is going to be 9 liters and final will be 12. So that's before and after on volume. Then the before pressure is 2 atmospheres and the final pressure will be P1V1 equals P2V2. You saw it for the final pressure. So that's what this one does. So if we start with that one and make this one vacuum, then this solution will give us 1.5 atmospheres from this gas into a vacuum. And we do the same thing for the other side. Okay. The gas 2 solution, that's supposed to be an X or a dot, pressure times volume. We do that same solution. Here we've actually just solved the equation for the unknown, and then we plug into that. And that's going to be 0.75 atmospheres from this one expanding into a vacuum. Now the total, the combined pressure is 1.5 plus 0.75 is 2.25 atmospheres. And that's what we thought it would be, somewhere between 2 and 3. Okay, well, that's where we pause for today. And we'll pick that up next Friday and finish off this chapter. And then the following Friday, we'll finish off chapter 8. And then the following Friday, we'll do a review.